There are two methods to run a significance test. In the first method, you will state the hypotheses. The null hypothesis is a statement you want to disprove. In the null hypothesis, HO, you should make the claim that the population proportion P equals some number P0. The alternative hypothesis is a counterclaim that you want to prove true. The alternative hypothesis, HA, should make the counterclaim that this population proportion does not equal some specific number. In the second method, we'll look at ways to test whether it's less than or greater than this number, but for right now, we'll just say it does not equal the number. Then you want to check assumptions. Your assumptions should be simple random sampling, 10 successes and 10 failures or more in the sample. Be aware that there are two types of errors that can occur in significance testing. A type 1 error rejects the null hypothesis when it's true. Alpha is the probability of a type 1 error. A type 2 error fails to reject the null hypothesis when it is not true. Your fourth step will be to form the appropriate confidence interval. And then finally, based on this confidence interval, you will make a conclusion. Bobby Joe Long, born October 14, 1953, is an American serial killer on death row in the state of Florida. Long abducted, sexually assaulted, and murdered at least 10 women in the Tampa Bay area during an 8-month period in 1984. He released his last victim, Lisa McVeigh, after sexually assaulting her for a period of 26 hours. In the American legal system, Bobby Long was assumed innocent until proven guilty. Let's set up our null and alternative hypotheses. The null hypothesis, HO, is the statement we want to disprove. We would like to disprove that Bobby Long was innocent. The alternative hypothesis, HA, is the statement you would like to prove true. We would like to prove that Bobby Long was guilty. Let's use this to fill out the table below. If the null hypothesis is true, then Bobby Long would be truly innocent. And if the null hypothesis is false, then Bobby Long would be truly guilty. The decision made using information from the sample would be equivalent to the decision made by the jury. The jury could fail to reject the null hypothesis, meaning that the jury could find him innocent. Or the jury could reject the null hypothesis, meaning that the jury finds him guilty. If Bobby Long was truly innocent and the jury finds him innocent, then no error has been made. If the jury finds him guilty and he's truly guilty, then no error has been made. However, if we reject HO when HO is true, if the jury finds Bobby guilty when he was really innocent, then this is a type 1 error. And if you fail to reject HO when HO is false, if the jury finds Bobby innocent when he is truly guilty, this is a type 2 error. You should use this table to help you write out the type 1 and type 2 errors. I'll write these on the next page. So I've written that the type 1 error is that the jury finds Bobby guilty when he's truly innocent. And the type 2 error is that the jury found Bobby innocent when he was truly guilty. Out of the two errors, I think we could all agree that we would rather the type 2 error to occur. It would probably be better to let a criminal go free than to send an innocent person to jail. So we will probably allow the type 2 error to occur a little more frequently than a type 1 error. Now what if we lower the type 1 error all the way to 0? So we could say that Bobby must be found not guilty. That way we never send a truly innocent person to jail. Now the flip side of this is that when you look at the type 2 error, if you always find Bobby not guilty, that means the type 2 error must occur. The jury would have to find him innocent even if he was guilty in order to avoid the type 1 error. So they play off of each other. So the idea is we'd like to come up with some kind of number to control the type 1 error. And that number would be the significance level alpha. Alpha is the probability of a type 1 error. And the common alpha levels are 0.1, 0.05, and 0.01. These correspond to confidence levels. Your confidence level is 100 times 1 minus alpha. 1 minus 0.1 is 0.9. 0.9 times 100 is 90%. So an alpha of 0.1 goes with a confidence level of 90%. A significance level of 0.05 goes with a 95% confidence level, and a significance level of 1% goes with 99% confidence. According to the results from a Gallup poll 1 decade ago, the proportion of U.S. citizens that support the death penalty was 80%. Among the groups most supportive of the death penalty were conservatives, Republicans, men, and older respondents. Since this time, many school shootings such as the Newtown, Connecticut shooting have occurred. After the Newtown shooting, a random sample of 1,000 U.S. citizens was taken, and the number of citizens supporting the death penalty was 835. Is there evidence that the proportion of U.S. citizens supporting the death penalty has changed? Use a 90% confidence level. Our first step in running a hypothesis test is to set up the null and alternative hypotheses. These statements are about the population proportion P. We don't know the value of P, but we know in words P is the proportion of U.S. citizens supporting the death penalty, or from up here, the proportion of U.S. citizens that support the death penalty. Now, what we would like to disprove is that it is still 80%, and what we would like to prove is that it has changed. The second step in running a hypothesis test is to check your assumptions. We need simple random sampling, and it says a random sample was taken. The next assumption is that n times p hat is greater than or equal to 10. N times p hat is the number of successes. It's the number of people who said yes. And if you look, out of the 1,000 people, 835 said that they support the death penalty. This is your n times p hat. You also need 10 or more failures. N times 1 minus p hat should be greater than or equal to 10. But you could think through this one as well. If there's 1,000 people and 835 said that they support the death penalty, then 1,000 minus 835 would leave over the people who don't. This is also clearly bigger than 10, so our assumptions have been met and we can proceed. Next, we form the confidence interval, and we need to use a 90% confidence level when we do this. The formula for the confidence interval is p hat plus or minus z alpha over 2 square root of p hat times 1 minus p hat divided by n. P hat is your number of successes out of the number in the sample. Here, 835 said yes out of 1,000 in the sample. This is 0.835. And that's the number we'll plug into all the p hat positions in the confidence interval. N is the number in the sample. Here it says that 1,000 citizens were sampled, or you could think of it as the denominator from your p hat. We'll plug this into the n position of the confidence interval. A 90% confidence level corresponds to a z.1 over 2, or a z.05. And we know that this number is 1.645. We'll plug this number into the confidence interval as well. When you do 0.835 minus 1.65 times this square root, that will give back 0.816. And when you do 0.835 plus 1.65 times the square root, that will give back 0.854. Now that we have the confidence interval, we're ready for the final step of our hypothesis test, and that's to write the conclusion. So here's how you decide how to write a conclusion. If P0 is in the confidence interval, then it's likely that P could equal P0, so you should fail to reject the null hypothesis. And a conclusion you could write is at the alpha significance level, we fail to reject HO and conclude there is not enough evidence to, and then state HA. If P0 is not in the confidence interval, you should reject the null hypothesis. It's not likely that it equals this number. And in this case, you would say at the alpha significance level, we reject HO and conclude there is evidence of HA. Then you should also make the statement, in fact, we are 100 times 1 minus alpha % confident that P is less than or more than this number from the null hypothesis. Let's see what happened in our example. Here, P0, the number from the null hypothesis, is 0.8. If you compare 0.8 to this confidence interval, you see that 0.8 is less than 0.816 and also less than 0.54. It is not contained within the confidence interval. If the number from your null hypothesis is not in the confidence interval, then you reject HO. It's not likely that the true proportion would equal 0.8. As a matter of fact, it's likely that the true proportion is different from 0.8. So let's use this to write a conclusion. Using our general statements, we can say, at the alpha % significance level, if we had 90% confidence, then alpha is 10%, or 0.1. So at the alpha equal 0.1 significance level, we reject HO and conclude there is evidence, and then we want to state HA. So looking at our problem, seeing that we should say HA says that P, the population proportion, the proportion of U.S. citizens supporting the death penalty, is not equal to, is different from 0.8, or 80%. So we can now finish our conclusion. We reject HO and conclude there is evidence that the proportion of U.S. citizens supporting the death penalty is different or has changed from 80%. That takes care of this part of the statement. When we say that it changed from 80%, we didn't specify whether the change was an increase from 80% or a decrease from 80%. So now we could come in and specify whether the new value is less than or more than P0. And for us, P0 is 80%. According to the confidence interval, the true proportions should be somewhere between 0.816 and 0.854. And we're actually 90% confident that this value will be in this interval. So we're 90% confident that this proportion is larger than 80%. In fact, we are 90% confident that, saying P in words, that the proportion of U.S. citizens supporting the death penalty is, and then choose either less than or more than, we chose more than, is more than 80%. Remember, 80% was your P0. Here's a second example. According to the Bill and Melinda Gates Foundation, 30% of college students graduate from two-year institutions on time. The college dean wonders whether the percent of students at her college who graduate on time differs from 30%. She obtains a simple random sample of 500 records of students who have graduated and finds that 165 graduated on time. Does this represent significant evidence that the percent of students at the Dean's College who graduated on time differs from 30%? Use 95% confidence level. Our first step is to set up the null and alternative hypotheses. Both of these hypotheses will be about the population proportion, the proportion or percent of students at the Dean's College who graduate on time. We don't know what the true percent is, but we would like to disprove that it's 30%, and we would like to prove that it's some number not equal to 30%. Our second step is to check assumptions. We need simple random sampling, and it says that she obtained a simple random sample of 500 records. We also need 10 or more successes. We see that out of these 500, 165 students graduated on time. And if there's 500 students total that were sampled, and we take out these 165 who graduated on time, that leaves over less than 400 students who didn't graduate on time. This number is also greater than 10. Now that we know that our testing assumptions have been met, we can form the confidence interval. The formula for the confidence interval is p hat plus or minus c alpha over 2 square root of p hat times 1 minus p hat divided by n. P hat is your number of successes in your sample. Here P hat, or X over N, is the success of the 165 students who graduated on time out of the 500 students total. This is 0.33, and we'll replace all the P hats in the confidence interval formula with this value. The next item we could get to plug into the formula is the sample size, and we see that 500 student records were recorded. Lastly, we should get Z alpha over 2. Here, because we're doing a 95% confidence interval, we know we're looking for Z.05 divided by 2, or Z.025. We should have memorized that this is 1.96. This is the value we'll plug in for Z alpha over 2 in our confidence interval formula. If you do 0.33 minus 1.96 times this square root, you will get back 0.28. And if you do 0.33 plus 1.96 times this square root, you will get back 0.37. This is our 95% confidence interval. We're now ready for the fourth step, make a decision. If you take the number from your null hypothesis, the idea that the true percent who graduate on time equals 0.3, and see if 0.3 falls into this confidence interval, you will find that 0.3 is indeed a number between 0.28 and 0.37. It is indeed contained in the confidence interval, so it's likely that the proportion could equal 0.3. Therefore, you should fail to reject the null hypothesis. There is a chance that the proportion could equal 0.3. If you fail to reject the null hypothesis, that means you have to say that it's likely the true proportion could be 0.3, which means you could not prove the true proportion was different from 0.3. Let's use this to write our conclusion. At the alpha significance level, and here because we had 95% confidence, we know the alpha that goes with that is 0.05. We fail to reject HO and conclude there is not enough evidence to prove, and now we need to state HA. So we said there is not enough evidence to prove that P, the percent of students at the Dean's College who graduate on time, is not equal to, differs from 0.3, 30%. So at the alpha equal 0.05 significance level, we fail to reject the null hypothesis and conclude there is not enough evidence to prove the proportion of students at the Dean's College who graduate on time is different from 30%. Here are the works cited for this lecture.